this module we will look at glazing and shading system. So far we have talked about the opaque component, opaque wall system. Here we will look more closely into the glazing and shading system. So we will talk about thermal properties of glazing, which is important. Then the next thing we will talk about is shading system, designing shading system primarily. So what determines the thermal efficiency of glazing system? This first thing of course is thermal transmittance of glass, same as we talk about wall, thermal transmittance U value of wall. The most commonly referred thing is thermal transmittance of glass. The next important factor is solar heat gain through glass. This is a important factor which ranges from 0 to 1. We will look at this factor more closely. This tells you how much amount of radiant heat gets into the particular system apart from the conductive heat transfer. Next thing is thermal transmittance of the frame, which is nothing less than less important than the glass itself. It is also crucial. And the last thing is the air tightness of the glass frame assembly, how well your glazing system is sealed. If you have a lot of infiltration, as we discussed in the previous modules, we will have heat gains and losses, hot air coming in. As when you heat your building, the hot air will go out, there will be heat gains and losses which is not intended. So in that case your cooling load or heating load will considerably go up. So 4 parameters are there, apart from other things 4 are very crucial. First is the U value or thermal transmittance of the glass, second is the solar heat gain through the glass, third is thermal transmittance of the frame, and the last is air tightness of the glass frame assembly. First, the glazing U value, which we commonly know, the first property usually we refer to, it is a heat transfer through conduction, as we saw same as the your opaque wall system as well. It tells you how much amount of conductive heat flow happens through the glazing system. Say imagine you have a single glass system, you have a 6 mm glass, single glass system, versus you have an air gap and you have a double glass system, you have a DGU or double glass unit. So 6 mm, this is 12 mm, another 6 mm. So as you increase the number of layers or a triple glass system, another layer, then you will keep the U value starts coming down. It essentially tells you how much conductive heat flow happens. So this matters. Then the next conductive property of this air gap, or if it is inert gas filled like argon filled, then this brings down your U value. Further the next layer, next layer, next layer, apart from the film coefficients outside and inside. So the more number of layers or the thickness of glass itself varies, or the type of infill, whether it is air or an inert gas like argon filled, then your U value considerably reduces. An air air filled versus argon versus a vacuum insulated system, the U value considerably comes down. Apart from this, then another important factor is the solar heat gain coefficient, that is SHGC, commonly referred as SHGC. Some of the older codes or test standard refer it as SC or shading coefficient. We will look at the relation. It simply gives you the ratio of solar heat gain through the glass relative to the incident solar radiation. So what happens when the solar incidence happens on the glass? It is a proportion of the solar energy directly transmitted as well as absorbed and re-emitted. So moment you have the long wave solar radiation, the short wave solar radiation hitting your glass, then it absorbs, first partly it is transmitted, then some of it is absorbed and then retransmitted, each layer retransmits it. Effectively it is given using a number called SHGC or solar heat gain coefficient. It ranges from 0 to 1, the lesser or more closer to 0, it it tells you the efficiency of the glazing system. So today we talk about highly efficient low emissive glazing system, we will talk about them, but they will have SHGC more close to say something like 0.15 or 0.25. This will be efficient system, versus you will have something like 0.7 or 0.8 for single clear glazing system. So which means more amount of radiant heat is getting transmitted into the space compared to this particular glazing system. So how does it matter? Imagine you are designing a building in a colder climate, a place like Srinagar where the ambient is getting really close, inside you are heating the building. The primary mode of heat transfer which is of importance is the heat conductive, because you are heating the building, you do not want the heat to be lost outside. Ambient is really cold, or imagine the outside is frozen, it is at minus 10 degree, you are heating your building, say inside is plus 20 degrees, ambient is at minus 10 degrees. So the gradient is inside to outside. In this case you are heating it, in the ambient it is snow. Conductive heat loss takes the primary thing. On the other hand, during summers you really want more direct solar heat gain to come, because the temperatures are not going to go very high, except for certain extreme cases where both summer as well as winter are both harsh. Mostly the summer sun is always welcome, so you want more glazing surface, the radiant heat is welcome. So in that case you will want the U value as a primary indicator. SHGC is also important because you do not want your building to get overheated, as we looked at the greenhouse effect where the glass is more transparent to short wave solar radiation, but when the internal surfaces absorb and start re-emitting it, it is opaque to it. So the heat gets trapped inside, which is called greenhouse effect, which we do not want to happen. So in that case we try and restrict the radiant property or the radiant transfer through the glass as well. Imagine you are designing in a hotter climate or a hot season where the indoor is at 24 degrees, you are conditioning it to 24 degree, ambient is at 45 degrees. You have a glazing system, similarly you have a double glass system. So essentially what happens, you have a lot of, apart from conductive heat gain, you also have a direct solar heat gain, which considerably impacts the radiant gain and the cooling efficiency and comfort indoor. So while you design for hotter climate or hotter seasons, in fact solar heat gain coefficient becomes a crucial factor. There is a lot of difference if you take a particular Indian location, any location, most of it is warm or hot locations except for the northern belts which is really cold. Solar heat gain coefficient has higher impact compared to U value. Most of the tests and the experiments we conducted, we found a higher impact. Say for example, when I am reducing a solar heat gain coefficient from 0.8 to 0.2, there is a drastic reduction in the cooling energy, as well as the improvement in comfort is also much higher compared to reduction in U value. U value is also crucial, but solar heat gain coefficient takes the front seat if you are designing for a hotter location. It is improved by two different things. First is, if you are able to minimize or cut off the direct solar radiation. You have sun here, if you have a shading device which is cutting the solar incidence, then you can actually improve the performance. Actually you are not doing much to the glass, here still the conductive heat flow will happen, whereas you are cutting off the direct solar incidence, so your radiant transfer will be minimized. This is an indirect way of controlling the solar heat gain through the window. So for this case we do not look at SHGC of just the glass or the window alone, but we look at something called a composite SHGC where the glazing and shading together is accounted for. Other way of looking at it is to go for selective or spectrally selective coating, where we talk about low heat glasses, low emissive glasses. So instead of providing a shading system, here I am trying to give you a solution where, for example, this is a commercial building facade where the designer is not interested in providing shading system. This is your building, this is in, this is out. You apply a specific coating on this particular glazing system, a low E coating. Essentially it is a silver coat with certain nanoparticles associated. What this does is, this is spectrally selective. As we know, solar radiation has a wider spectrum from ultraviolet to visible to infrared, solar radiation is on short wave infrared and then the re-radiation is on long wave. This particular coating will be, this can be applied on this surface or this surface, there are variations associated. We generally do not do the coating here because of wear and tear, same reason here, it can be done on this face or this face. What essentially this does, this coating allows visible radiation while it reflects the short wave. The short wave radiations are reflected back while the visible spectrum is allowed in. That means it allows light to pass through, but it cuts down the short wave radiation. If you go back 25-30 years back in time, moment when people realized that this clear glass or clear glazing system are highly radiative, they have a lot of radiant heat gain, they started using a coated glass or a tinted glass. Essentially it is a mix bronze or some kind of metal which is mixed in the glass, so the glass gets darker. As a consequence, what happens, the light transmittance through the glass came down drastically. Say when I said 0.7 or 0.8 for a clear glass, the light transmittance or visible light transmittance, that is VLT, here will be around 75%, that is 75% of light is transmitted into the building, which will actually help you in reducing your lighting energy or lighting loads. So number of lights can be less or less lights can be turned on, whereas when you want to reduce this particular thing, instead of going for a spectrally selective coating, if you are going for a tinted glass, a dark colored tinted glass, say a bronze colored glass, then your SHGC might come down, say instead of 0.7 it can go to say 0.5, whereas your visible light transmittance becomes 30%. So only 30% of the available outdoor light can come into your building, whereas this has come down marginally. So there is an improvement here, but this is leading to a problem. On the other hand, when you use a low E coated or a spectrally selective glazing, this does not happen. Even for a glazing with 0.2 SHGC, you may be able to get a VLT or visible light transmittance up to 50-55%, or with modern day coatings it can even be higher. It depends on the type of products or the coating material which is used. The conventional way of referring was shading coefficient. Some of the data sheets still refer shading coefficient because some test standards are able to demonstrate shading coefficient. SHGC is a factor of shading coefficient. You can for a quick working you can multiply it by 0.85. When I said spectrally selective coating, this is what actually happens. This is a demonstration illustration which I referred from another book, textbook. This is a total solar spectrum. It starts from ultraviolet, you have a visible spectrum, and then this is a solar infrared. This is a transmittance of a system. What happens with the spectrally selective coating? This particular spectrum is reflected back while this particular spectrum is allowed. So if you take wavelength, it allows the wavelength in this range while it considerably blocks. Say this is clear glazing, it allows a lot of daylight, but it also allows short wave radiation. Number 2 is a bronze tinted glazing, it cuts down drastically on the light, visible light transmittance, but it also cuts little bit on your short wave radiation. So here for clear glass it is around 85% visible light transmittance, whereas it is 85% solar radiation transmittance, short wave transmittance also. On the other hand, if you go for a spectrally selective or low E coated, this is number 5, you get a visible light transmittance as high as 80%. You can minimize the short wave or solar radiation transmittance up to 15 or 20%. It varies, as I said, depending on the coating and the tint of the glass as well. So this is more effective in controlling. But one thing we need to note, with the effect of coating it is possible, but apart from this, by the use of shading system also, by cutting down the source itself, that is direct incidence, by avoiding using this particular strategy, it is also much effective. If you are willing to go for shading system, it is much more effective and economic to provide improved efficiency for the glazing system. I have referred one of the commercially available catalogs, this corresponds to one company. There are a lot of glazing companies, everybody has an extensive data sheet. One of these things Typically if you look at a brochure, you will have commercial names which is essentially not important in this section. We will have solar transmittance, visible transmittance, solar transmittance and UV transmittance. Some of them give this but not all. Here we have visible, so this particular glass 76% visible transmittance, solar transmittance is 48%. Reflectance, out and in reflection, this actually gives you an idea about whether a particular glass, say it may be a see through glass, but still you will be able to see the reflections of your own self when the other side is not that bright. Imagine you are working in an office in the night time, you will be seeing your own images if the inside reflections are higher. Then there is a U value which is for winter, again it is specific standard, some of them give you winter summer U value, different test conditions. When you say U value, typically you will get NFRCR, National Fenestration Rating Council of US standard tested U value. So there is a set outdoor temperature and set indoor temperature for which the U value is calculated. Some calculation procedures require you to test for different conditions also, but most of these brochures, data sheets that you get correspond to NFRC standard tested U values. Then you have shading coefficient and SHGC. Let us take this first glass, it has a visible transmittance, it is a clear glass, 76% visible transmittance and about 60% or 0.59 solar heat gain coefficient SHGC. On the other side, take another glass where you have an SHGC of 0.22, that is you have brought down the SHGC to pretty less than half of what it was here. The U value more or less remains the same, with air it is 0.3 U value, here it is 0.3 again, U value did not change, but the SHGC has considerably come down. Please remember the U value does not significantly get affected when you do a low E coating. It is essentially a reflective coating. Please recollect the type of thermal insulations we talked about. We have resistive insulation which is given by U value. Here we are talking about reflective insulation which is SHGC, effect of coating, where you have brought down the efficiency, brought up the efficiency pretty higher. Solar heat gain coefficient or the radiant cutoff for radiant has been brought to 0.22. The visible transmittance also has gone down, but there are also some other glasses where you have more or less a trade off. You can see for all of them the U value remains the same, while the SHGC considerably varies depending on the coating. Depending on this, the visible light transmittance also considerably varies. So what are the major challenges? Yes, we have an exhaustive data sheet, more or less all the glass manufacturers would give you an exhaustive data sheet where you will have series of numbers, most of them you may not even look at or take as a criteria for selecting. Yes, 2 or 3 crucial parameters you will look at and you will choose a glass, but what are the challenges practically? The first major challenge is what you get from this data sheet is something called center of glass U value. So if you have a glass like this, you have frame all around, this is your glass. In this case what actually happens, the value that they give you, they would have tested this glass panel through typically a hot plate apparatus that I was talking about. So essentially the value, the U value that they give you is something called center of glass U value, somewhere taken corresponding to what happens in this. The edge effects are the effect of the interaction with the typical frame system is not considered. There is a minor difference, though it is not a huge impact, but still there is an impact between the center of glass U value to edge of the glass U value. Number 2, the need for U value of the frame itself. Imagine you have a UPVC frame versus an aluminum frame versus a highly insulated thermal barrier aluminum frame, or different type of structural facade system versus a non-structural facade system with thermal insulation, without thermal insulation. So see, you have a highly insulated glass here. If the frame itself is not thermally insulated, then you will have a lot of gains and losses happening at this particular juncture. So this particular things become a weaker link, this will create problems for you. Number 3 is computation of whole assembly U value. So imagine the next step hurdle you have crossed, you have the glass U value, you also have the frame U value. Now how do you compute the whole assembly U value? Do you think for each of these combinations, so you have chosen a frame out of 1000 options available and you have chosen a glass out of 1000 glasses available in the market, do you think somebody is going to test the whole system and give you? No. For specific projects, for larger projects, you might be required to test, in the laboratory a glass frame assembly also. Some sophisticated projects, depending on the requirements, might demand you to test this as well, but some of the projects you can compute them. If a standard, good tested value, reliable value is available for glass and frame, then it is possible to compute the whole assembly U value. Again, please remember, here we talked about the material level property, here we are talking about the assembly level property. The next important thing is the effect of shading system on SHGC. Naturally, you buy this from a separate company, this is sold by a separate company, and essentially when you have a shading system, that is sold by a separate company. So whose, either it is a hand, cast in situ shading device, concrete or masonry shading device, or it may be a aluminum or steel section which is available, like louvers or blinds that you are going to install. So the effect of this particular shading system on the glass is another crucial thing which needs to be accounted. Apart from all this, whether we are doing steady state computation, a particular instance in which U value and SHGC are determined versus the dynamic site performance. What happens to the solar movement, what happens to the insolation versus how much is getting transmitted is highly dynamic. These are challenges, but with all this, the industry has proceeded much faster, so we have more or less standard values available. Just to give you a better picture of what I have been talking about, two different frame systems, this particular frame versus the other one. I am not getting into details of what frame it is and what they actually mean, but typically the heat transfer through this frame is relatively higher compared to this, and the effect of different frames, actually we took 10 different glasses, 5 different frames, and how much amount of energy saving happened. Yes, glass has a lot of impact compared to this versus this, the savings has gone up, say here you get about 8 to 9% saving, whereas you get around 1 to 2% saving in this particular glass. But what we need to note, even with this glass, if you go for an efficient frame, you can go as high as 4% energy saving. Even if the glass is really good, if the frame isn't good, you will lose 1.5 to 2% of your estimated energy saving. So frame has a crucial role in the effect of the energy efficiency, impact of the overall system. How do you design shading device? A quick overview of the processes involved in designing shading system. We have looked at the solar charts. What I have superimposed here, in a following session I will also demonstrate how to compute this using certain tools, but to take a quick look at it, you have a solar chart, sun path diagram. This is for Bangalore. The window size is 2400 by 1200, this is facing south. So you see a thin set of grey lines, it gets darker as it goes here. This is on December 21st, that is winter solstice. So this particular window, which is, imagine the window is located here, there is a shading system, a simple horizontal shading device 450 mm thick, it is going to cast a set of shadows. After a while you will not get much shade, when the sun is here you will get shade. So this typically gives you a estimate. I will show you more details about this. This is for a west facing, the same window located on a west facing wall. Take a closer look at this. This is a uniform overcast sky, the amount of shading, the percentage efficiency of the shading. Percentage shading is 40% for a south facing wall with a 450 mm shading device, whereas almost you get no shading if it is a west facing wall. Yes, horizontal shading devices are not effective, we will look at more in detail. The conventional method of calculating shading was using a shadow angle protractor and sun path diagram. Typically this is like, you have radial lines marked 0 at the center and goes up to plus 90 and minus 90. Then you have these arc lines, they coincide with the altitude angle, and here it coincides with the 90, plus 90 and minus 90. You typically mark the duration and time in which, season and duration in which shading is required. You put this over, superimpose it, and then I will show you some examples of how to do this. But before that, few angles are important. We need to recollect azimuth is, this is like a trigonometric projection of the 3D sun movement on 2 dimension. It gives you the azimuth angle on which orientation relative to north or south where the sun is located, and altitude tells you, relative to the horizon at what angle the sun is located. Shading system requirement vary with respect to climate, latitude, longitude of a place, facade orientation and typical shading requirements. Apart from this altitude and azimuth angle, we have three other important parameters. One is the wall or surface azimuth angle, that is to which particular orientation the wall is tilted to, can be referred from north or from south. Then you have something called horizontal shadow angle and you have something called vertical shadow angle. We will look at these two things more in detail. The horizontal shadow angle is a difference between the azimuth of the sun's position and the wall orientation, that is wall azimuth and the solar azimuth. It gives you the difference, that is effectively it takes into consideration the orientation of the wall surface. So this gives you the horizontal shadow angle, the difference actually gives you the horizontal shadow angle. So how to understand this? If horizontal shadow angle, see if this is a line drawn, this actually gives you how much projection you need. So the lesser the horizontal shadow angle, this line converges and this projection is going to come farther ahead. So this is a vertical shading system. The effectiveness of a vertical shading system is given by horizontal shadow angle. So if you have to, this is for example a south facing surface, you have sun moving from this side to this side. As this gets further, the cutoff duration increases. So you want, for example 8 am in the morning to 6 pm in the evening, you want cutoff. The depth of this overhang, the vertical shading device, this is a plan view, this will further deepen. So the cutoff will be more. Similarly for the afternoon hours. Alternately, if you want the cutoff only from 10 o'clock in the morning to 3 o'clock in the evening, this can be shorter. Or if the latitude of the place, if you do not get deep southern sun, this can be lower. If the sun is just passing on like this, then you may not need a deep vertical overhang. This is as far horizontal shadow angle is considered. It is nothing but solar azimuth minus wall azimuth. Once you have this number horizontal shadow angle, you can actually find out what is a PV, that is the projection depth, the depth of the projection required, for which you will need the window dimension. Mostly you will have the window dimension in this formula, then you will know the left hand side. So I know what is the width of the window, say imagine I have a 2 meter long window, then I only do not know what should be the projection required. So to know this, you will take this in this side, it will be the width of the window by tan horizontal shadow angle. So the horizontal shadow angle gets to the denominator, the lesser it is, the deeper the shading you are going to get. The next is a vertical shadow angle, this is a reverse of it, it is more or less the altitude versus the cutoff. So the lower the altitude of the sun, you are going to get more solar incidence on your window surface. So the vertical shadow angle will vary accordingly. Similarly, a lesser vertical shadow angle, this is taken between the horizontal plane and the range where you need the cutoff. It can be same as altitude angle provided you want to cut off the whole of the sun. If you do not want sun on this particular day, then your shading device will be this deep. For example, you have a window, this is a south oriented window, sun is here during October you have sun coming here. So you want a cutoff, you have provided a shading system like this, then in December, this is October, in December you are going to get sun at this point, you may not want to cut off the December sun, so you can just curtail your shading system at this point, so you will be getting sunlight during December. But if you further want this to be cut off even during December, then you need a deeper shading system. As the vertical shadow angle comes down, the shading depth increases, similar to what we saw in the previous example. Same as that, if you will know the height of the window, what you need to know is the depth of the projection, you will know what is a vertical shadow angle. Once you know the vertical shadow angle, you can determine the cutoff and how much width is required, or alternately if you know the width, you can find out what is a shadow throw, how much shadow this is going to throw on a particular fenestration. Apart from this, another small step which is needed in shading calculation, even if you provide a proper horizontal shading system, if the sun is moving from this end to this end, then you will have sun getting from the sides. So to cut this off, you need a slight projection. There is a formula here, the depth or A dash I have mentioned here, this particular depth shown in the red line can be given by width of the horizontal shading into tan horizontal shadow angle. This will give you how much projection extra is required. So, if you have a window this long, whether I should curtail it here or should I extend it further, and if so, how much extension is required. This particular depth, that is A dash, which I have mentioned in the formula, is given by this simple equation. How do we go step by step? First is determine the cutoff date. You take a solar chart, determine the cutoff date to which you need, you want to exclude sun, and start and end time, whether you want it for all through the sunshine hours or specific duration. Say you want from 9 to 1:30 or say 4 o'clock in the evening for our ease of working. Let us say 9 to 4 o'clock in the evening we want cutoff on a particular day, up to a particular day. Then calculate azimuth and altitude angle, calculate the shadow angle, and further estimate the width and depth of shading system. To show you graphically, the first step is 9 o'clock in the morning to 4 o'clock in the evening. I am saying this is a south facing wall, so I want to exclude sun all through the year up to December 21st, up to winter solstice. I will prefer excluding the sun. The altitude, I have taken Delhi as a location, the altitude on that particular extreme. So, I have to find out the extreme case December 21st at these points 1, 2, 3, I have to find out. Altitude angle and azimuth angle are known. Sun's position, this is at 9 o'clock, this is at 4 o'clock in the evening, same altitude and azimuth angle is determined. Next, determine the shadow angle, horizontal and vertical shadow angle. Once I determine what is the horizontal and vertical shadow angle, as I said, I know the window height and width. With that I can calculate the projection which is required horizontally as well as vertically. So, this is a traditional way of calculating. Another approach using computational tools I will be demonstrating in one of the following sessions. If you take a code like energy conservation building code, which is more commonly used for building applications today, it gives you a very simple approach or simplified approach rather. You may not be able to precisely find out the shading projection and depths for any specific location, but overall it gives you two conditions. One is north latitude 15 degrees or greater and less than 15 degrees north latitude, that is below 15 degrees and above 15 degree. Two specific instances are given and 4 orientations are addressed: north, east or west and south. First thing is, it asks you to calculate something called projection factor, which is nothing but this versus the vertical. How tall is your window plus the small gap that you provide here, the masonry you provide here, and what is the depth, this particular thing. Usually you will want to determine this, so the formula turns the other way. Then if you know the projection factor, you can substitute it here. For different projection factors you have something called M factor, or which is needed for the shading calculation. So, once you know the projection factor, they give you how much amount of M factor is given, is taken from this table. If you substitute, then you will get a desired amount of shading depth. What I will do in the subsequent section, I will demonstrate a software with which you can determine the shading and one or two worked examples using this projection factors as well. So, we looked at the thermal properties of glazing, what is important, glass frame and assemblies. Then we looked at shading systems, typically what angles are involved and how do we design a quick estimate of the shading depths, vertical and horizontal shading devices. Thank you.